Okay, this is going to be a relatively short video where we go over how we're going to apply Newton's laws to allow us to solve problems. So to start, I've got an example here. I'm going to push a block with a force of 10 newtons, and the block is sitting on a ramp, so I've got a picture here. Sitting on a frictionless ramp. We're going to push parallel to the ramp surface, so we're going to be pushing in this direction. What is the acceleration of the block? And so here's my picture in the first step in force analysis problems. And the reason we know this is a force analysis problem is because we're asked what the acceleration is. And to figure out acceleration, we're going to need to leverage Newton's second law, right? We need to find the net force. And before we can find the net force, what we want to do is we want to draw a free body diagram. And so I've got my picture here. Immediately, I sketch out a free body diagram. So I've got my coordinate system aligned with the ramp, so parallel and perpendicular to the ramp. I am pushing up the ramp. The weight, of course, is straight down towards the center of the earth. And then there's a normal force perpendicular to the ramp. So these are the three forces that are applied to the block. There's no friction in this case because we were told that the amount of friction between the block and the ramp is 0. Now, when we've got our free body diagram here, the next step is to check to see if any of the forces that we've drawn are not aligned with the x or y axis. And so if we look at the weight here, we need to break up the weight into components that are along the x and the y axis. And so last thing I want to point out is the ramp angle here is 30 degrees. So when you go to sketch this free body diagram, the angle here between the weight vector and our y-axis is 30 degrees as well. So that's going to allow us to redraw the free body diagram. The normal and the push force are exactly the same, but now I've decomposed the weight vector. There's an x component, so that's w sine 30. So if you look over here, it's that component. That's why it's sine. And then along the y-axis, we've got w cosine 30, and that's that vector. So here is our free body diagram that is ready for us to now go straight into Newton's second law. So we've got a picture, then we've got a free body diagram. Now we're going to apply Newton's second law. And so in Newton's second law, we've got the net force in the x direction is equal to, well, let's look at our diagram. I've got the push in the positive direction. So what I do, instead of writing the vector push, I've done a plus sign because I know that's the direction of the force, and then just the magnitude of the push force. I do the same thing with w sine 30. It's to the left, so I need the negative sign, and now I've got the weight times the sine of 30. Now those are the only two forces along the x-axis, so I'm done. That's got to be equal to max. Now, let's pause there and write out Newton's second law for the y. So read these off. We've got the normal up, and then we've got the weight, the component of the weight perpendicular to the ramp, so minus w cosine 30. Now that's got to equal may, which, since the block is sort of constrained to move along the ramp, the y acceleration has to be 0. And so that tells us that the normal force equal to the weight times cosine 30, which is mg cosine 30. In this case, I think we are done with the y analysis, that there's nothing else that we can do there. We're going to move back to the x analysis. So if we look at the x analysis, we've got our push force minus the component of the weight down the ramp equal max. So what's my push force? Well, it was 10 newtons. Again, the plus is because it's up the ramp. Minus mg sine 30. And that's got to be equal to max. So here I'm going to plug in everything. Plus 10 newton minus 24.5 newton equals 5 kilogram times ax. So this means that ax is equal to minus 2.9 meter per second squared. The minus sign here is telling me that the acceleration is in the negative direction. So this is the direction of the acceleration, down the ramp. So even though we're pushing up the ramp, the component of the weight down the ramp is so much larger than how much we're pushing that the block is going to accelerate down the ramp. So basically, you need to get out of the way because this block is going to run you over. Okay, and another thing that is going to be very helpful to us as we start to solve force problems is to go over some details for specific forces. And so the first force I want to talk about is tension. So tension exists in a problem anytime you have a taut string, cable, rope. Tension is always a pulling force, and unless otherwise stated, the tension is going to be the same everywhere along the rope or the cable. So take, for example, this picture down here. I've got a block connected to another block by a string over a pulley. So this is one string here. So in our simplified model for the tension in a string, the tension is going to be the same up here as it is down here. It's the same amount everywhere. It just so happens that for the block over here, tension is always pulling, so there's tension to the right. This block here, there's tension up. And so depending on what object you're talking about that's connected to the string, that tension force may be in different directions, right? So you have to pay attention to that. Another thing that's sort of related to tension has to do with pulleys. So if your pulley is massless or frictionless, then pulleys only serve to change the direction of the tension force. And so right now, in our introduction to forces and using our simplified approach, our pulleys are going to be massless and frictionless. And so what that means is that all the pulley does is change the direction of the tension force. All right, so we're also going to deal a lot with friction. And so friction comes in a few forms or versions. And so we've got static and kinetic friction. And so I've got the little text box here from the book. If two surfaces are stationary relative to each other, so stationary relative to each other, then that we get static friction. And if two systems that are in contact are in relative motion, then it's kinetic friction. Right? So basically, if you think two surfaces at rest relative to each other, static friction. Two surfaces in motion relative to each other, kinetic friction. Now, the amount of friction that exists between surfaces depends on a few things, but one of the things that it depends on is the type of surface, the type of surfaces that are in contact. And this gives rise to something that we're going to use throughout all of our friction problems called the coefficient of friction. So there's coefficients of static and kinetic friction. So this is sort of pronounced mu sub s, mu sub k. So if you look in table 6.1 in the book, there's a list of coefficients for various surface contacts. So like rubber and concrete, like wood and wood. Each of those combinations results in a different coefficient of static and kinetic friction. Now, static friction, again, exists any time that two surfaces are not in motion relative to each other, so that they're at rest relative to each other. Static friction, it turns out, is not a single value. Static friction essentially depends on the situation. Static friction, the amount of static friction that exists between two surfaces is essentially the amount needed to keep the object at rest. But there's a limit here. There's a maximum amount of static friction that can exist between two surfaces. And so that maximum amount of static friction is mu s, so whatever the coefficient is, times the normal. So in the given problem, what's the normal force that your object in question is experiencing? So static friction has a range of values that it can take on depending on the scenario. The smallest value of static friction you can have is 0. So if there's no friction required to keep an object at rest, then the static friction is 0. If the object would move without friction than there is static friction that's present. And there's a maximum amount of static friction that can be generated for any given situation. Now, kinetic friction, that corresponds to when two surfaces are moving relative to each other. Kinetic friction is a set value. So whatever the coefficient is between those two surfaces, and then multiplied by the normal force. If you look at the table, mu s, the static friction coefficient, is, I believe, I'm not actually looking at the table at the moment, but I believe mu s is always larger than our mu k values. And so what that tells you is that essentially if your object is at rest, it would take more force to get the object moving than it would once it starts moving. Then the kinetic friction is less. It takes more force to get it moving than it does to keep it moving at the same constant speed. And the last thing that I want to mention is centripetal force. And so remember, we talked about in two-dimensional motion, centripetal acceleration. That's acceleration that's associated with changing direction as opposed to changing speed. And so when we have an object in uniform circular motion, then we call whatever the net force on that object is, we call that centripetal force. And so whatever net force gives rise to uniform circular motion, that is, for that particular problem, referred to as the centripetal force. Now, if you recall, centripetal acceleration in magnitude is v squared over r. So the magnitude of centripetal force is just ma, so mv squared over r. And so the typical approach when we're dealing with centripetal force is that we analyze the problem just like we would in any force problem. We find the net force, and then we recognize that there's uniform circular motion, so we set that net force equal to the centripetal force, mv squared over r. And so, again, same approach. You would free body diagram to Newton's second law, and then at that point with Newton's second law, when you set up m equals a, you would plug in v squared over r for the acceleration. So that's when you've got an object experiencing a variety of forces but is undergoing uniform circular motion. You would leverage this fact that the acceleration, if it's undergoing uniform circular motion, the net acceleration has to be v squared over r, so that net force has to be what we call centripetal force. And you'll see some other forces, right? There's drag force that's going to show up, and a few others. But I think using these sort of details or tips about friction, about tension, you should be able to set up and begin to tackle most of the problems that we're going to look at in Chapter 5 and Chapter 6, dealing with forces.